Hey everyone, and welcome back today. We're embarking on arguably the most epic journey imaginable. We're not just looking at the stars, we're going to understand how they got there. We're going to witness the birth, life, and evolution of galaxies, the colossal cities of stars that fill our universe. Imagine, if you can, a time, before stars, before planets, before even atoms. We're talking about the Big Bang. About 13.8 billion years ago, everything we know, everything that exists, was contained in an unbelievably hot, dense point. Then BAM! Not an explosion in space, but an expansion of space itself. For the first few 100,000 years, the universe was a chaotic, opaque soup of fundamental particles, too hot for light to travel freely. It was like living inside a star. But as it expanded, it cooled. And then, around 380,000 years after the Big Bang, something profound happened. The universe cooled enough for electrons to combine with protons and neutrons, forming the very first stable atoms, mostly hydrogen and helium. And just like that, the universe became transparent. And the light from that moment, that first light, is something we can still detect today: the cosmic microwave background radiation. It's literally the afterglow of creation. Now here's where it gets really interesting for our story. This CMB isn't perfectly uniform. There are tiny temperature fluctuations, infinitesimally small variations in density. These aren't random noise. These are the cosmic fingerprints of gravity at work. These tiny density bumps, these slightly more crowded neighborhoods in the early universe, are the seeds from which everything we see today would eventually grow. Think of them as the very first tremors of structure. Without these initial imperfections, the universe would be a boring, uniform soup forever. But thankfully it wasn't. And it's these tiny variations that gravity would begin to exploit, patiently, relentlessly, for billions of years. This is where our journey truly begins. So we've got a universe that's mostly hydrogen and helium, expanding and cooling. But what happened next? For hundreds of millions of years, not much, at least not visibly. This period is appropriately called the Cosmic Dark Ages. No stars had formed yet, so there was no light apart from that fading glow of the CMB. Imagine endless, cold, dark emptiness. Pretty bleak, right? But beneath the surface, gravity was still doing its thing. Remember those tiny density fluctuations? Those slightly over-dense regions started to pull in more matter. But not just normal matter, the stuff that makes up stars and planets. This was primarily a mysterious substance we call dark matter. We can't see dark matter. It doesn't interact with light, but we know it's there because of its gravitational influence. It acts like an invisible scaffolding, a cosmic web of gravity, pulling in normal matter along with it. So during the Dark Ages, these dark matter halos were quietly growing, creating gravitational wells, silently collecting the hydrogen and helium gas around them. As gas fell deeper into these dark matter wells, it compressed, it heated up. And eventually, in the densest hearts of these nascent structures, the pressure and temperature became so immense that something truly groundbreaking happened. Hydrogen atoms fused into helium. The first stars were born. We call them population 3 stars, and they were nothing like our sun. These were colossal, monstrous stars, hundreds of times the mass of our sun, burning incredibly hot and bright. Because they were so massive, they lived fast and died young, exploding as supernovas within just a few million years, and their death was as important as their birth. These supernovas didn't just scatter the hydrogen and helium. They forged and then scattered the very first heavy elements, things like carbon, oxygen, iron, elements that are absolutely essential for forming planets, and eventually us. This era, when the first stars and quasars began to light up the universe, is known as the epoch of ionization because their intense UV radiation stripped electrons off atoms, clearing the cosmic fog. From a universe of pure darkness, the first pinpricks of light appeared, forging the very building blocks of complexity. This was the true beginning of cosmic structure. We've seen the first stars ignite within the embryonic dark matter halos. Now let's scale up a bit. These initial dark matter structures weren't isolated. They were part of a vast interconnected network, the cosmic web. Imagine it like a colossal, three-dimensional spiderweb stretching across the entire universe, with massive clusters of galaxies at the nodes or intersections, and long, thin filaments connecting them, with vast, empty voids in between. dark matter and gas flowed along these filaments, drawn by gravity towards the densest regions, those initial overdensities we talked about. These smaller knots in the web became what we call mini-halos. These mini-halos were essentially the first gathering places, the first neighborhoods where stars could really start to congregate. Within these mini-halos, gravity continued its relentless work. As more gas accumulated, it began to collapse into denser clumps. These clumps, much like the first stars, would eventually ignite, forming the second generation of stars, richer in those heavier elements forged by the population 3 stars. These new stars weren't just individual pinpricks of light, they were starting to form in groups. This is what we call a protogalaxy. Not yet the grand spirals or majestic ellipticals we know, but rather messy, irregular clumps of gas, dust, and these newly forming stars. Think of them as cosmic toddlers, still wobbly, still figuring things out, but definitely growing. These protogalaxies were much smaller than today's galaxies, maybe tens of thousands of light years across, and these protogalaxies weren't static. They were constantly interacting, pulling on each other gravitationally, feeling the tug of their neighbors, and crucially, merging. This merging process is absolutely fundamental to galaxy evolution, and we'll be coming back to it throughout this script. It's like these cosmic toddlers were constantly bumping into each other, and sometimes joining forces. Each merger was a dramatic event, often triggering bursts of star formation as gas clouds collided and compressed. These early mergers were the engines of growth, allowing these small protogalaxies to gradually build up more mass, attract more gas, and begin their long journey towards becoming mature galaxies. So, we've moved from scattered stars to the very first rudimentary collections of stars and gas. The universe is slowly but surely building its first major structures, piece by messy piece. All right, let's talk more about our invisible architects, dark matter. We've established that dark matter forms the gravitational scaffolding, but its role is far more profound than just providing the initial seeds. Dark matter halos are essentially the cosmic cradles in which galaxies are born and evolve. Imagine a giant invisible sphere of dark matter, maybe hundreds of thousands or even millions of light years across. This halo provides the deep gravitational well that allows ordinary baryonic matter, the gas and dust that make up stars, to collect and cool. Without this immense gravitational pull, the gas would simply be too hot and too diffuse to ever collapse and form stars on a large scale. As gas falls into these halos, it doesn't just plummet straight down. It often has some initial rotation, some angular momentum. As it loses energy and collapses, this angular momentum causes it to flatten out, like a spinning ball of dough flattening into a pizza. This is a crucial step towards forming the characteristic disk shapes of spiral galaxies. The dark matter halo acts like a massive centrifuge, helping to organize the gas. Another key aspect, dark matter halos are much larger than the visible galaxies they contain. Our own Milky Way galaxy, for example, is maybe 100,000 light-years across, but its dark matter halo is estimated to extend for hundreds of thousands of light-years. The visible galaxy is just the luminous tip of a much larger, invisible iceberg. Another key aspect, dark matter halos are much larger than the visible galaxies they contain. Our own Milky Way galaxy, for example, is maybe 100,000 light-years across, but its dark matter halo is estimated to extend for hundreds of thousands of light-years. The visible galaxy is just the luminous tip of a much larger invisible iceberg. And speaking of interactions, the growth of dark matter halos isn't smooth. They constantly grow by accreting more dark matter from the surrounding cosmic web, and by merging with smaller dark matter halos that contain smaller galaxies. This hierarchical merging process is fundamental. Small structures form first, then merge to form larger ones. So, dark matter isn't just a placeholder for stuff we can't see. It's the dominant gravitational component in the universe, dictating where and how galaxies form, shaping their evolution, and even influencing their ultimate size and structure. It's the unseen hand guiding the entire cosmic dance. All right, let's talk about our home. The kind of galaxy you probably picture when you think of a galaxy, a grand, majestic spiral. Our very own Milky Way is a spiral galaxy, and they are incredibly common and beautiful. But how do they form? We touched on it earlier. The key to a spiral galaxy is a rotating disk. As gas cools and falls into a dark matter halo, it brings with it a certain amount of angular momentum. It's already spinning a little bit. As it collapses, this spinning motion intensifies, much like a figure skater pulling in their arms. This causes the gas to flatten out into a thin, rotating disk. Now let's talk about a very different kind of galaxy, the ellipticals. If spirals are the bustling, active cities, then ellipticals are the grand, ancient monuments. They are often giant, smooth, football-shaped or spherical collections of billions of stars, but they look very different from spirals. Notice the color difference. Ellipticals are predominantly reddish or yellowish. This tells us something crucial. They are mostly made up of older, cooler, lower-mass stars. They have very little new star formation happening, and consequently very little gas and dust, the raw material for new stars. They are essentially retired star factories. So how do these cosmic relics form? The leading theory is that most large elliptical galaxies are the result of major mergers between two or more spiral galaxies. Imagine two grand spirals colliding. It's not like cars crashing. It's a slow-motion dance over hundreds of millions of years. The stars rarely collide, but the gravitational forces are immense. When the gas clouds from the two spirals collide, they compress violently. This triggers an absolutely ferocious burst of star formation, burning through vast amounts of gas in a relatively short period. This starburst phase can be incredibly luminous, but eventually, this gas is either used up in new stars or, just as often, it's heated and expelled from the nascent elliptical galaxy by powerful feedback from supernovae and the central supermassive black hole. What's left behind is a galaxy mostly devoid of gas and dust, with a chaotic, randomized stellar motion, stars moving in all sorts of directions, not in an orderly disk. This random motion is a key characteristic of ellipticals. Think of it like a cosmic mosh pit compared to the organized carousel of a spiral. Smaller ellipticals might also form through different processes, like harassment in dense galaxy clusters, where tidal forces strip away gas. But the really massive ellipticals are almost certainly the end product of grand cosmic collisions. They often reside in the most crowded parts of the universe, at the centers of galaxy clusters, where mergers are more frequent. So, while spirals are busy building new stars, ellipticals represent the final, quiescent stage for many massive galaxies. A monument to cosmic violence that has, paradoxically, settled into a serene old age. We've talked about the elegant spirals and the majestic ellipticals, but the universe is also full of galaxies that defy easy categorization. These are the irregular galaxies, and they are the cosmic wildcards, messy, disorganized, and often full of vibrant star formation. Our own Milky Way has two prominent irregular companions, the Large and Small Magellanic Clouds. These are gas-rich, active star-forming galaxies, but they don't have the grand spiral arms or the smooth, symmetrical shape of an elliptical. They just are. Their stars and gas are jumbled, often in clumpy formations, so why are they so messy? Often it's because they're undergoing or have recently undergone interactions with larger galaxies. Tidal forces from a nearby massive galaxy can rip apart a smaller one, distorting its shape, pulling out streams of stars and gas, and preventing it from ever settling into a neat disk or spheroid. These gravitational interactions can also trigger intense bursts of star formation. When gas clouds are compressed by tidal forces, they collapse, leading to a frenzy of new stars being born. That's why many irregulars, especially the Magellanic Clouds, are teeming with young, blue stars and glowing nebulae. Some irregulars are essentially galaxies caught in the act of merging, like the famous antennae galaxies, where two spirals are ripping each other apart, flinging out long streamers of stars and gas. They are a snapshot of a violent cosmic dance. There are also what we call dwarf irregulars, which are some of the most primitive galaxies in the universe, believed to be remnants from the early universe. They are small, faint, and gas-rich, and might be some of the building blocks that formed larger galaxies. Irregulars are fascinating because they represent the universe's ongoing process of assembly and transformation. They show us that galaxy evolution isn't always a smooth, orderly progression. Sometimes it's chaotic, violent, and utterly beautiful in its disarray. All right, let's talk about the absolute behemoths at the heart of most massive galaxies, supermassive black holes. These aren't just fascinating curiosities. They are incredibly powerful engines that profoundly influence the formation and evolution of their host galaxies. Every major galaxy we've looked at closely, including our own Milky Way, harbors a supermassive black hole at its center. Our Milky Way is called Sagittarius A star, and it's about 4 million times the mass of our Sun. Other galaxies have black holes billions of times more massive. When these supermassive black holes are actively feeding, that is, when they're drawing in vast amounts of gas and dust from their surroundings, they become incredibly luminous objects called quasars, or active galactic nuclei, AGN. The material falling into the black hole forms an accretion disk, which heats up to millions of degrees, emitting prodigious amounts of radiation across the electromagnetic spectrum, sometimes outshining the entire rest of the galaxy. These quasars were much more common and brighter in the early universe, which tells us that supermassive black holes were feeding much more actively when galaxies were young and rich in gas. They are like cosmic beacons showing us where the most intense galaxy growth was happening. But here's the crucial part for galaxy evolution. This isn't just a one-way street of the black hole consuming gas. The powerful radiation, and especially the incredibly energetic jets that often blast out from the poles of these active black holes, can have a devastating effect on the surrounding galaxy. We call this feedback. This feedback can literally blow vast amounts of gas and dust out of the galaxy, or heat it up so much that it can no longer cool and collapse to form new stars. This process effectively quenches star formation, halting the growth of the galaxy and helping to transform a gas-rich star-forming spiral into a gas-poor, red and dead elliptical. The remarkable thing is that there's a strong correlation between the mass of a supermassive black hole and the mass of the central bulge of its host galaxy. This suggests that the black hole and the galaxy grow together, constantly influencing each other. They're not just independent entities, they're intrinsically linked partners in evolution. So supermassive black holes are not just cosmic drains. They are powerful regulators of galaxy growth, playing a crucial role in shaping the evolution of the largest structures in the universe. They're the cosmic overlords, if you will, dictating the destiny of their galactic empires. We've mostly talked about individual galaxies or small groups, but galaxies aren't evenly distributed throughout the universe. They clump together into vast structures called galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, along with immense amounts of hot gas and, of course, dark matter. These clusters sit at the nodes of the cosmic web, the densest regions where gravity has pulled together the most matter. Our own local group, which includes the Milky Way and Andromeda, is just a small galaxy group, but it's part of a larger supercluster called Laniakea. Now, what happens to galaxies when they find themselves in these crowded, high-density environments? Their evolution is profoundly affected. One striking observation is that rich galaxy clusters tend to have a higher proportion of elliptical galaxies and fewer spirals, especially towards their centers. Why, one major factor is called ram pressure stripping. Clusters are filled with incredibly hot diffuse gas, the intra-cluster medium. As a galaxy moves through this gas at high speed, it's like a cosmic headwind that strips away its own cooler, star-forming gas. Imagine running with a wet umbrella in a hurricane. The water gets ripped right off. Without their gas, spirals can no longer form new stars, gradually turning red and dead, perhaps even transforming into ellipticals. Another factor is tidal harassment. In the dense environment of a cluster, galaxies are constantly experiencing strong gravitational tugs from their neighbors. These tidal forces can disrupt their internal structure, trigger starbursts, or even remove stars and gas again, pushing them towards an elliptical morphology. You even see jellyfish galaxies carry spirals with long, glowing tails of gas streaming behind them, clear evidence of ram pressure stripping in action. These are galaxies caught in the act of being transformed by their environment. And of course, in these dense environments, galaxy mergers are more common. So the cluster environment is like a cosmic pressure cooker, accelerating the evolution of galaxies, often turning active star-forming spirals into quiescent, older ellipticals. It's a powerful example of how a galaxy's destiny isn't just about its internal properties, but also about its cosmic address. One of the most incredible things about astronomy is that looking far away in space is also looking back in time. Light travels at a finite speed, so when we look at a galaxy billions of light years away, we're seeing it as it was billions of years ago. This allows us to do cosmic archaeology, digging through the layers of the universe's past to understand how galaxies formed and evolved. Telescopes like the Hubble Space Telescope, and now especially the James Webb Space Telescope, are our ultimate time machines. JWST, with its incredible infrared capabilities, can peer back to the very first galaxies that formed only a few 100 million years after the Big Bang. And what do we see when we look that far back? We don't see grand, majestic spirals like our Milky Way. We see small, often clumpy, irregular galaxies furiously forming stars. These are the protogalaxies, the cosmic toddlers, still in the chaotic process of building themselves up. These early galaxies were much smaller, but they were incredibly active, churning out stars at a much faster rate than galaxies today. They were undergoing frequent mergers, constantly smashing into each other, growing in size and complexity. The universe was a much more violent and dynamic place back then. As we look forward in cosmic time, meaning closer to us in space, we start to see the emergence of more defined spirals and ellipticals, testament to billions of years of mergers, gravitational collapse, and the influence of dark matter and supermassive black holes. This cosmic archaeology confirms our models of hierarchical galaxy formation, the idea that small structures form first and then merge to build larger, more complex ones. It's not just theoretical. We can actually see it happening through the universe's own timeline. Each new generation of telescopes allows us to push the boundaries of this cosmic exploration even further, revealing more about the very first moments of galaxy assembly and how our universe came to be filled with the breathtaking structures we see today. It's an ongoing, thrilling scientific detective story. So we've journeyed from the Big Bang to the present, witnessing the birth and evolution of galaxies. But what about the future? Our cosmic story isn't over. It's constantly unfolding. And for our own Milky Way, the future holds a truly spectacular, yet utterly transformative event. In about 4.5 billion years, our Milky Way galaxy is destined to collide and merge with its nearest large galactic neighbor, the Andromeda galaxy. It's already headed straight for us. This isn't a crash in the traditional sense. Stars are so far apart that individual stellar collisions will be extremely rare, but the gravitational forces will be immense. As the two galaxies pass through each other again and again, their gravitational fields will rip them apart, fling out streams of stars, and violently compress vast clouds of gas. This will trigger a colossal burst of star formation, unlike anything our galaxy has seen in billions of years. The night sky for any intelligent life existing then would be utterly breathtaking, filled with new nebulae and young bright stars. Eventually, after hundreds of millions of years of this cosmic ballet, the two spiral galaxies will settle down into a new single, much larger galaxy. And based on what we know about mergers, it's highly likely to be a giant elliptical galaxy. We'll be shedding our spiral arms to become a smooth, reddish, quiescent relic, and it's not just us. The universe on its grandest scales is still evolving. Galaxy clusters will continue to grow, accreting more galaxies and dark matter. The most massive black holes will continue to feed and grow, but the accelerating expansion of the universe, driven by dark energy, will also play a crucial role. Eventually, billions of years from now, all galaxies beyond our local supercluster will recede from us so quickly that their light will never reach us. They will effectively disappear over the cosmic horizon. The observable universe will become a much emptier, lonelier place. Our descendants, if they exist, might look up at a sky with only the Milky Way galaxy and a few nearby dwarf galaxies, with no clue of the vast cosmic tapestry that existed before. It's a sobering thought, but it highlights the dynamic, ever-changing nature of our universe. From the smallest fluctuations in the early cosmos to the grand collisions of galaxies and the eventual lonely future, the story of galaxies is one of continuous transformation. Wow, what a journey, right? From the incredibly hot, dense moments after the Big Bang, through the cosmic dark ages, the birth of the first stars, the chaotic assembly of protogalaxies, the stately dance of spirals, the violent mergers creating ellipticals, and the shaping power of dark matter and supermassive black holes, we've seen how the universe built its grand cities of stars. And in every step of this journey, gravity has been the master sculptor, patient and relentless, working with the raw materials of hydrogen, helium, and dark matter. We've learned that galaxy formation isn't a single event. It's a continuous process, driven by accretion, star formation, stellar death, and perhaps most dramatically, by galactic mergers. So when you look up at the night sky tonight, and you catch a glimpse of the Milky Way, or if you're lucky enough to spot Andromeda, I hope you'll see it with new eyes. You're not just seeing billions of stars. You're seeing the culmination of billions of years of cosmic history. You're seeing a galaxy that has grown, merged, and evolved through unimaginable forces. And think about this. The very atoms that make up your hand, the carbon, oxygen, iron in your blood, these were forged in the hearts of those first colossal stars, scattered by their violent deaths, collected by protogalaxies, nurtured in stellar nurseries within our ancestral galaxies, and eventually gathered into our sun and earth. We are literally stardust, formed within these magnificent cosmic structures. Our existence is intimately tied to the grand story of galaxy formation and evolution. It's a story of chaos and order, of creation and destruction, all playing out on the grandest stage imaginable. And the incredible thing is, we're still learning. Every new telescope, every new observation adds another piece to this colossal puzzle. Thank you so much for joining me on this epic journey through cosmic time. If you enjoyed this deep dive, please hit that like button, subscribe if you haven't already, and let me know in the comments what other cosmic mysteries you want to explore next. Until then, keep looking up and keep being curious. This universe is waiting to be understood.